So this brings us to the issue of how we can see atoms. See, as we discussed in the previous slide, if we know the position of the object inside the unit cell, in principle, let's say this is an object inside a unit cell and we sent in an X-ray beam. If we know the positions of these atoms, this edge of the elbow or leg or whatever, then it is possible to reconstruct the image by getting the amplitudes of the scattered radiation and doing a Fourier transformation. Lens is not possible, but we do the Fourier transformation, get the information of the position of the atom which is being present already. But what happens is that we do not know where the atoms are, and that is the job. So there are two unknowns here. The positions of the atoms are not known, the associated phases are not known. So in fact we can't get the image. So we have to either guess the position of the atoms, which is what was done in the earlier days of structure determination, or guess the phase position, and then we have to get to the this one, the image of the object. So how do we go about it? We go about it in such a way that the image reconstruction has to be monitored by actually solving the phase problem. Now how do we solve the phase problem? We solve the phase problem by guessing what the phases are. That's the only way we can get to the image of the object, which means the positions of the atoms. So how do we really see atoms? This is a picture which I have taken from the book of Glusker and Trublet, a remarkably good quality book, which I suggest that all of you go through it. Here this is a picture from the older version of Glusker and Trublet. As you can see that we here have written photographic film. In modern days we do not use the photographic film, we use different kinds of modern day detectors like the CCD cameras or the EOS and so on, the photon detectors and so on. Nowadays very high quality detectors are there to measure this. So what is the thing we need to construct? You see, if we have the knowledge of the phase as well as the amplitude information, like in the case of a normal microscope where we have the visible light as the probe and visible light falls on an object, the object scatters radiation in all possible directions and we take now this scattered radiations and put a convex lens in front of it, the so called objective lens, we get an image of the object. So the main object generates the image just like the previous slide we had, and this image of course can be made to enlarge by what is known as an eyepiece lens, and this now enlarges the image. So suppose let us say this was a piece of the bread which we had, and I put this here and put it under a microscope. I will get an enlarged image of the object of that piece of bread, and you see some of these little pieces here that could be the pieces which we talked about in terms of cashews and badam and things like that. So effectively we see the enlarged image, and therefore we get an information about the nature of the object much better, and this is how the typical microscope works, a light microscope. We can use of course different kinds of radiation and make the corresponding microscope. We can use electrons and make an electron microscope, and we can use the electron microscope to fall on the object. Scattering will occur. Now instead of the lens we can have a measuring device like a CCD or something. So in this particular example we are using X-rays. The object is the crystal. Now one of the properties which the crystal has, which I have not mentioned so far, which you have learned so far but I have not mentioned it, is the fact that there is a systematic arrangement of objects inside the crystal, and this is governed by symmetry. And because it is governed by symmetry, the scattering occurs not in all possible directions, but scattering occurs in only predetermined directions, predefined directions depending upon where the nature of the crystal. So we have, let us say, the crystal lattice known, we know where the equivalent points are, we know what are all the atoms which are there in the system. In principle what we measure are the scattering which is coming from individual crystal planes, and therefore It is not in all possible directions, like our interference experiment told. If you have two slits, the two slit experiment gives you the interference pattern, dark and bright images. If it is a three-dimensional one, you get spots, weak and dark spots, and therefore you don't get the continuous scattering as it happens here, but you get discrete directions. Now the fact that this happens in discrete directions helps us to identify the spots. So we can identify the spots, we can also identify the coordinates of these spots, and when we identify the coordinates of these spots, then we identify the nature of the way in which these spots are distributed, and this is referred to as the reciprocal lattice, because what we get is before the image reconstruction, and we get the intensities of each and every spot, which is the intensity of the reciprocal lattice point. Then we solve the phase problem by some means and do a Fourier synthesis using the help of a crystallographer in earlier days, but nowadays it is only computer which can do the job. So we do not need a crystallographer. We just do these computers, use the computer and do the image reconstruction, and then once we do that, we will get the image of the object. The image of the object now, just like here we saw all the additives, we will see the positions of the atoms. What we see are not the positions of the atoms per se, we see the so called electron density distribution. The heavier the atom, the more is the electron density, the lighter the atom, the less is the electron density. So you get what is known as an electron density map. So this in a nutshell tells you what we do in X-ray diffraction techniques. So we have a crystal, the crystal obeys all the rules which we have formulated for the symmetry information, and therefore the scattering occurs in only specified directions. These specified directions now can be caught on a screen. It could be a photographic film, it could be a detector. Then we do the image reconstruction through Fourier synthesis after solving the phase problem, and we get the image of the object. So to recapitulate again, we have a crystal, X-rays are falling on the crystal. The crystal now will scatter only in certain specific directions. We will find out what are those specific directions in the next couple of classes. And then these now create dark and white images. We can say the so called reciprocal lattice will be created, because we have a lattice in the crystal lattice will now create the reciprocal lattice. We have just seen why it should be reciprocal from the previous diagrams. And therefore, this reciprocal lattice information can be now used. We measure the intensity of every one of the spots. We also estimate the phases associated with these spots. We measure the coordinates of these spots in reciprocal space and then do a Fourier synthesis after guessing what the phases are, and then we get an image of the object. And the crystallographer will do the manipulations and the changes that are required based on the Fourier synthesis in order to get a final electron density map. And this can be now done through computers. We have the synthesis Fourier refinement programs where we improve the phase information such that we get to the final electron density. So what we get finally is the electron density map, the distribution of electron density associated with atom positions. Wherever there is an atom, we have a large amount of electron density, as you all know, and therefore depending on the strength of the electron density, we can also find out which atom is what, and therefore we get the entire structure. And the structure now will come in a situation of a single unit. Under the single unit cell, we know the equivalent points, and therefore we can determine the structure associated with the asymmetric unit. So what we eventually look for is the structure that is associated with the asymmetric unit in the unit cell. Right. So how is the whole thing done? So this is the whole logic of how this whole thing has been carried out. So let us go through it very slowly and systematically. So when electromagnetic radiation passes through a crystal, so we now have a crystal, we are sending electromagnetic radiation, now we know it is X-rays. So X-rays are falling on the crystal or matter in general. As we discussed so far, the electrons are the ones which are perturbed that are disturbed by the rapidly oscillating electric field. Since these electrons are now connected to the nuclei, the nucleus and the electron density gets disturbed in such a way that the positive and the negative signs there is a displacement, and this displacement causes a dipole, and this dipole now oscillates with the incoming radiation, and therefore it emits its own radiation. And we have already made an assumption, as I mentioned, that it is coherent scattering. So, there is no change in the frequency after the scattering experiment is done. So, we shall take the electric field as E naught cosine 2 pi nu t, and if we take that as the electric field or the electric disturbance which occurs at the origin, and now whenever it falls on that object, we have to see when and where it falls on the object. So, what is happening is that these now emanate as spherical waves, as we saw from the previous diagrams where we had an object and a slit experiment. So, these emanate as spherical wavefronts. In general, instead of using only the real part, we also bring in the imaginary part of the axis. It is mainly because electromagnetic radiation and the theory of electromagnetism essentially involves complex waves. Waves expressed as cosine plus I sine. So, E naught is therefore E naught e to the power of I 2 pi nu t. So, the exponential I 2 pi nu t can be expanded further into E naught cosine 2 pi nu t plus I sine 2 pi nu t. So, it is a cosine and a sine function, and therefore, we write this what is known as the Argand diagram, where we have the imaginary axis along the y direction and the real axis along the r direction. So, suppose we have two waves E1 and E2, and they are now coming out from this system, and E1 is at a phase which is delta 1 and E2 has a phase which is delta 2. Then these two now will combine, and the way in which the resultant is taken is very well known in mathematics. So, we take the resultant, and the resultant of these two waves E1 and E2 is E, which is now has a separate phase which is delta. This can be in fact illustrated with a diagram here. So, if we now say that this is the E1 and this is E2. So, depending upon the phase associated with E2, this wave will develop either constructively or destructively, as it happens here. So, this particular wave now is overlapping at different positions along the incident wave, or we can take this wave as E1, which is emanating from the origin, which is the electron density position, and E2 is another wave which originates from some other atom, but we associate that with the origin. Then we can combine E1 and E2 and get the average, the resultant associated with E1 E2, and therefore, you see that if this is the phase associated with E1 delta 1, this is the phase associated with delta 2, then we see that the phase associated with this will be delta, which is a combination of delta 1 and delta 2. So, if we consider it that way, we go back to that picture and we see therefore, we have an E1 and an E2, the resultant vector is along the E direction, and so this is the corresponding delta value. What is happening in a scattering experiment is one more issue which we have to consider, that is the issue of what we see and where it happens. Because if the electrical disturbance is associated with, let us say, E naught exponential I 2 pi nu t, and that is occurring at a particular origin 0 0 0, and then we actually look at what happens at a distance which is capital R from the origin. This particular wave which we are now talking about, which is now a complex wave, it spreads at a velocity of light. So, it spreads at the velocity of light and it spreads as a spherical wavefront, both we have seen. And at sufficiently large distances r, we have already decided it will be a plane wave. So, it will go as e to the power of ik dot r, where k is the wave vector and r is the position vector. So, that is associated with the amplitude E naught, and this will be the phase. So, the phase now, if it is real, is cosine 2 pi nu t, but since we are considering electromagnetic radiation, the phase will be exponential I 2 pi nu t. Now the frequency we are assuming is not going to change, and therefore even if we now look at a distance r, we are not looking at the disturbance which we are now looking at a disturbance which originated at a time t minus r divided by c, because we are now measuring the intensity at a position which is at a distance r from the source. So if this is the source and we measure the distance at a distance r, then it has already travelled that distance with the speed of light, and therefore what we are measuring is that which occurred t minus r by c before. Let me explain it a diagram. Suppose this is our position of the object, this is the position of the object from which this scattering is emanating. We are now measuring it at a distance, let us say r. So this distance is r now. So the wave front is spherical to start with, and somewhere here it is almost a plane wave. So as we measure it at a distance r, we are now sitting at this position and measuring. Now what we are measuring is not at t, but t minus r divided by c, because the wave started t minus r by c times before at that particular position. Let me make it clear again. What is happening is that if we are measuring at a time t with respect to the position r, we are actually looking at the wave which originated t minus r by c, where c is the wavelength, the velocity of light, and r is the distance at which it has travelled. So light has already travelled by that distance, and therefore this is therefore what is known as the path difference. This introduces a difference in path, and the path difference is now can be expressed in terms of wavelength as well, because c is equal to nu divided by lambda. So therefore we see that it is dependent upon lambda. So we introduce this expression. It is either 2 pi nu t minus r by c or 2 pi times nu t minus r by lambda, and this is therefore the extra path which it has travelled at any given time t. So the path that is travelled by the wave is covered by t minus r by c. So if that is the case, then we have to consider that as the so called path difference, or the phase so called phase difference. So if r becomes r plus delta r, and this delta r is very small, let us say. So if r becomes r plus delta r, then there is an increase in the path. Since this is t minus r by c, you see t minus r plus delta r by c, this is now the distance which has added a delta r to that, will make the value of the phase associated with that wave a little longer. So there is a phase difference which is negative here, and therefore the path difference is positive. So for every additional path, the phase difference is more. So as we keep adding, the phase difference will become more and more. So it is inverse of the two, and therefore we see that the expressions can be worked out now the way we have seen here. So we now look at the complex amplitude of the wave, the so called E naught. The E naught can be equal to if there is an electron density rho of r, if there is an electron density rho of r d of r that is present in space, let us say, and then you are sending in the X-ray beam. The X-ray beam is coming in this particular direction, and we call this quantity as S naught, which is the unit vector of the representation of the so called wave front. Remember, the wave front now, which originated as a spherical wave front, has become a plane wave. So therefore we are writing a single line here showing the wave front. So as the wave front approaches in this direction, we sit here at an origin and observe what happens to the presence of a little amount of electron density at this point. So we put a little bit of electron density there, and then the rays are coming in and we are sitting at this origin and observing what happens to that. As we have said earlier that the electron density now will change the direction of the wave. It will start its own wave and that wave will now originate in the direction p prime. So, the original one is going in the direction of p, this scattered one is going in the direction of p prime. So, now p prime will define the so called scattered direction. So, incoming direction is referred to by the unit vector s naught, the scattered direction is referred to by the scattering vector s. So, what is happening is the fact that whenever you find this electron density is located at a distance of r, little r, from the origin. So, we have an electron density which is located at a distance of r from the origin, and we see therefore that this wave travels an extra distance of r dot s minus s naught, r dot s minus s naught. So, since this travels an additional distance of r dot s minus s naught, this is the additional distance. This has travelled r dot s, it goes up like that, whereas the r dot s minus s naught is the additional distance. This will be the one which causes the phase change. So, the phase change therefore is 2 pi nu t, that is 2 pi I r dot s minus s naught divided by lambda. We are assuming that there is no change in the frequency. So, the frequency factor does not appear here, it is only the change in the path length. So, the change in the path length is introduced as rho of r exponential 2 pi I r dot s minus s naught by lambda, and this is occurring due to the presence of an electron density which is rho of r d of r. So, the E naught is equal to this quantity. The s minus s naught by lambda, we replace it by a capital R which we call as the scattering vector. We will look at some of the properties of the scattering vector as we go along. This scattering vector has dimensions of reciprocal length. Lambda is the wavelength. So, R has dimensions of reciprocal length. That means this scattering vector is something which could be a representation of the reciprocal lattice vector in some way. We have to find out what is the representation of capital R, because it is proportional to 1 by lambda. So, the fact that our image gets inverted after the scattering experiment is done using the analogy of a convex lens experiment of the light waves, we see R is proportional to 1 divided by lambda, and therefore, R could be utilized to define the coordinates associated with the reciprocal lattice. I am going to do this again one more round, so that there is no confusion associated with the understanding of this phenomena. This is the basic phenomena of scattering. So, this quantity R can also be, if you do a construction of this kind shown below here, S naught by lambda is the incoming radiation, S by lambda defines the scattering direction radiation, and then the scattering is due to the presence of the electron density which is rho of r d of r. Then the scattering vector is in a direction perpendicular to these two. So, it is actually a bisector of S naught by lambda and S by lambda, and I take this angle as 2 theta, then it is easily shown that modulus of r is equal to 2 sin theta divided by lambda, and this is the scattering vector. You see the scattering vector modulus is proportional to 1 divided by lambda, and therefore, this represents a quantity in reciprocal space. So, if little r is in the direct space where the electron density is located in our object, the capital R is the representation of the reciprocal lattice vector which corresponds to the real space vector R. The capital R arises because of the real space vector R having an electron density associated with it and a phase which is defined as exponential 2 pi r dot s minus s naught by lambda. And so, as a consequence, the path p prime, the extra path that is travelled is r dot s naught minus s. That means, when the wave is coming up here, it finds the electron density, it travels an extra path which is r dot s naught, that is because this is the perpendicular direction which we have taken. From here we draw another perpendicular. So, therefore, r dot s naught minus s is the path difference, and we have already seen the path difference being longer now the phase difference will be decreasing accordingly, and the decrease in the phase is 2 pi r s naught minus s by lambda, and that is what is substituted here. It is 2 pi r dot s naught minus s, the decrease in the phase. The decrease in the phase can be represented as s minus s naught by lambda, and therefore this is the path difference which occurs, and the path difference is a consequence of the definition of the scattering length. So r therefore is s minus s naught by lambda. We will study this in little more detail probably in the next class, but at this particular point we notice r is s minus s naught divided by lambda. And now we have to consider the entire crystal. If we consider the entire crystal, there is electron density distribution depending upon how many atoms are there inside the crystal. So what we do is we assume that the electron density is continuous in the entire crystal. It is not going to become negative 0 and all that. So we assume that even if it becomes negative 0 and all that, it is going to be a continuous function. Since rho of r is a continuous function, we therefore see that we can take the rho of r is the continuous electron density distribution. What all we have to do is to express the overall amplitude which comes out of the crystal. See, what is it we are looking for? We are now getting go back to this picture. We are getting the scattering coming from the crystal in a certain direction, and this particular direction is due to the scattering which occurred due to the presence of the electron density inside the crystal. And the presence of the electron density inside the crystal has now resulted in the change in the path length, and any additional path length results in decrease in the phase associated with the wave. And so we can calculate the complex amplitude, which is in fact, if we measure the intensity, the square root of that intensity will give us the amplitude. The complex amplitude can be calculated by this expression, and this is an expression which is associated with an element of space which is representing rho of r d of r. But if the electron density is continuous in the entire crystal space, this can now be obtained as the integration over the entire space, entire crystal. So the integration over the entire crystal of rho of r d of r, this is the phase factor, and this is the quantity which contributes to the overall complex amplitude, and therefore we get f of r, which is referred to as the scattering factor. Notice that this quantity f is a function of the scattering length r, and this particular scattering vector has the dimensions of a reciprocal lattice. So when we measure the so called intensity, we are actually measuring the intensity coming due to the presence of the reciprocal lattice point. So the intensity is coming from a reciprocal lattice point identified with respect to the scattering vector r, and therefore we get f of r, and this is a complex quantity again, and this is an integration over rho of r d of r, which is the overall electron density now inside the crystal, and this is the modification which gets introduced in rho of r d of r due to the fact that the object that is located inside the rho of r d of r, the atoms are located at different positions inside the unit cell. So you will get different phase changes causing these so called path differences, which are represented by the scattering vector r. So r is s minus s naught by lambda, and we get f of r is equal to this quantity. Let us go to the next slide and define find out the properties of f of r. We will do this derivation once again a little later in a slightly different way, so that it becomes very clear of how the scattering is occurring. But before we go to that, we just look at the possible properties of this f of r. F of r is a complex quantity, as we see already, and the intensity of the scattering, as I mentioned, is given by f r times f star of r. Now this f star of r is referred to as the complex conjugate. F r and f star of r in fact essentially define I of r. So if we measure the I of r and we take the square root of this quantity, we will in principle get the magnitude of f of r. In principle, the intensity and hence f of r modulus can be measured experimentally, therefore as a function of r. However, the phase angle associated, which is represented as exponential 2 pi I r dot r, is not an observable quantity. So, then of course, a special property of f of r is that if there is a if rho of r is real, f of minus of r can be written as f star of r, and the scattered intensity is unaffected by reversing the direction of the incident and scattered beams. Likewise, the same intensity pattern is produced by a given distribution of rho of r and by the distribution of rho of I minus of r obtained by inversion through the origin. That means when you have a inversion center and the electron density is measured, this inversion center will ensure that you will get a quantity which is actually a real quantity. So, f of r in that situation of a center symmetric positioning of the atoms will become a real quantity. So, if the that is what is written here, if the distribution rho of r is center symmetric, if rho of r is equal to minus of rho of r, let us say in P1 bar, then f of r is a real quantity. So, this again we will now refer to the organ diagram, and in the organ diagram we will represent what happens when there is a center of symmetry and what happens when there is no presence of an inversion center, and that is something which we probably will take up in the next class. So, at this moment, just to revise what we have done so far in this class, what I will do is we have taken the scattering issue and we have now considered the scattering process in detail. So, what we have done in this particular case is to look at two possible waves which are interfering with each other, two possible waves which are interfering with each other. One is represented by E1, the other represented by E2, and then the resultant one is represented by E. So, it depends upon what is the corresponding phase angles associated with E1 and E2.